Good morning, all of you. So we'll continue with the semiconductors. Today we are going to discuss about the p-type, n-type, p-n junction, and diode forward bias, reverse bias. This is a very core, you can say, the fundamental one. But if you look at the numericals, no, none of this theory, what I'm going to say, they don't go for that level of conceptual question. May ask. So here and there, that one. So the numericals are totally different. Like a similar to go for current density, apply KCL, KVL, you'll get the answer. But the theory here, little bit, you have to analyze at the molecular level, each and every electron, how it will flow, that one. Little bit difficult. I think most of you follow the SU Verma. I just will explore the SU Verma content in detail with the diagram, so that it'll be easy for you to understand what I'm saying. So don't refer. You can refer. I think somebody yesterday said Singage. It's there in content. Read Singage. Nothing there. Maximum, I'll focus on the SU Verma. The way he has explained, no, those ideas only. Let me just explain it in detail so that it'll be easy for you when you read SU Verma in my notes. No, almost it's going to help you with that one. So now, as yesterday we have seen, the conductivity of pure semiconductor, it was very low, no, and it was given by sigma is equal to charge yesterday. I think we have defined all these things. So these are the holes. H means hole, E means electron. Concentration of free electrons, and there's a concentration of holes, that one. Mobility, okay, we can't improve by a large quantity, that one. Leave that mobility. We can make changes, but the changes what we make practically what will not show much increase in the conductivity. What we are focusing, we are trying to increase the conductivity. What do you mean by conductivity? More current. I want to have more current through a diode. So now, is there any option of increasing number of electrons? Yes, it's their option in the semiconductor. You can increase either electrons or the holes. How to increase the electrons? By adding impurity atom. So next, first we'll define the term called as a doping. Adding an impurity atoms to an intrinsic semiconductor is called as a doping. This process is called as a doping. That one means how suppose when we cook some curry, we add some salt, no? So similar to that, adding some impurity items to a pure semiconductor. That's called a doping. By doping and pure semiconductor, we'll get an extrinsic semiconductor. So I'll increase any how much I want conductivity. Those many what happen, I'll increase this concentration at the level of electrons, the amount of electrons. So that will increase the conductivity. So what we have advantage, I can control the conductivity. This thing not there in metals. You can't change in metals. So whereas for electrons open, for semiconductors, yes, you can control. For copper, you see concentration of free electrons. It's a fixed value. You can't change it. For a metal, the conductivity is a fixed here. Of course, it will vary with the temperature, but altogether, I want to have some large change. I cannot produce. For semiconductors, possible both by varying number of holes, number of electrons. How do that? By adding impurity atom. For that, what I do, I'll take a pure semiconductor. This will be there's a pure semiconductor. What is the state? This will be the molten state. Not solid state, molten state. So germanium or silicon. Usually we prefer silicon. Let's assume it's the molten state. Here what happened? I'll add impurity atoms. This will also in molten state. And the moment I place it here, this particular liquid, molten liquid shall place it here, no, it will undergo diffusion because here concentration of impurity atoms, impurity is more, and what about concentration here less? So they'll start diffusing. If this is solid, I think not possible, no, they cannot mix up. So therefore, they will be in molten state. They may test with small ideas like this. So what we do is like for a pure semiconductor, for intrinsic semiconductor, which is there in molten state, I'll add impurity atoms which are there in molten state. Then due to diffusion, it will spread because the moment impurity atom comes here, number of atoms of impurity are more here, less. So therefore, it starts diffusing. So first, I'll go for construction of N-type semiconductor. So for this, what we do, we had pentavalent a pentavalent impurity atoms are added to intrinsic semiconductor. What are pentavalent impurity atoms? Like we have arsenic, antimony, and these are the some pentavalent and phosphorus. These are allied to pure semiconductor. What is the pure semiconductor? Either germanium or silicon. Let me take here now. What is the one? What is another condition? This impurity atom, it should exactly fit into the crystalline structure of semiconductor. Like that, what when the impurity atom shall pick up. And we know semiconductor is what? It's a tetravalent atom. Outermost orbit will have 4 valence electrons and it will share with adjacent atoms. So we'll get a covalent bond. So when I add such a pentavalent impurity atom, these are covalent bond it is. This is the impurity atom, phosphorus, I'll write it, and these are the silicon. Like that, a covalent bond will be formed. So, and these are the valence electrons. Phosphorus pentavalent atom, it's 4 outermost valence electrons it will use. It will share with the adjacent silicon atom. It will form a covalent bond. And what is one more condition? The impurity atom should exactly fit into crystalline structure. So like that, what happen after checking that one? So these are the some few what I indicated. They will exactly fit into crystalline structure of semiconductor. How much quantity next comes? What quantity of they should be added? For every 10 to power of silicon atoms, one impurity atom will be added. For every 10 to power of 6 semiconductor atoms, one impurity atom will be added. It will go and fit. So the phosphorus is a pentavalent impurity. So one electron weapon will be now loosely bound. It will be like this. So this you can show it like a red color only. It's a very loosely bound. So what is the energy with which it will be bound? 0.045 electron volt. So what will be the band structure? How the relative band structure will be? So if you look at the conduction band, there's a conduction band. and there's a valence band. Now, few, these are due to thermal agitation, and we'll get few holes that are generated due to thermal agitation. Next, what we have this donor level, no? It will come here. So these particular, for addition of one atom, one impurity atom, what happened? One electron will be available. Where do this electron will be available here? So let me show that this is called like a donor level. Why donor? So shall I say that that impurity atom donates one electron to the semiconductor substance material. So to donate addition of one impurity atom will make one free electron available. So what are these free electrons? They are due to thermal agitation. Due to this addition of impurity atom. So what is this energy? It will be binded by 0.05 electrons. So small, with small energy it will be binded. If you just supply that energy, that will become free, and it is free to move anywhere inside the material of semiconductor. So like this, for like if I had 1 gram of impurity atom, I think large number of electrons are available now. So then what I did, I just increased the conductivity by how much? By quantity of 10 to power of 8, 10 to power of 6 times. This is what happens in the semiconductor. Addition of one impurity atom will give one electron. So like this, let me add some 10 grams. In 10 grams of impurity atom, how many electrons are there? How many atoms are there? For one atom, one electron. So like this, you can see large number of electrons are available. This number will be far exceed than due to thermal agitation which are there. And where do they, this called a donor level, or you can also call this as a Fermi level. Just only remember, that's all. Don't go in detail. For n-type semiconductor, where Fermi level just below the conduction band. Okay, now how to show that? There's a thing. So there's a structure. So every time I'm not bother silicon. So this phosphorus, shall I say donor ion? Because it has given one electron, it has become donor ion. So how to show that semiconductor material now? How to show that semiconductor material? So we'll take this one, the material. So here afterwards, n-type semiconductor means so it has given one electron, no? So therefore that donor ion will show by positive sign. And each donor ion, so that electrons you show like this. And there'll be also few holes, no? Why do these few holes? These few holes are due to thermal agitation. So tell me like a OR majority here. OR majority. I think we can make a big diagram, no problem. Yeah. OR majority. So for n-type semiconductor, OR majority carriers. Electrons are majority carriers. So for n-type, this is n-type, I'll write it here. Like this, I'll indicate symbol. Majority carriers. OR minority carriers. O's, that one. I think this, not valence electron, free electrons. Or just you call electrons here. So for n-type, what happened? O is majority carrier. The free electrons are majority carriers. O's are minority carriers. Why do that O's? Due to thermal agitation. O's are not due to addition of impurity atom. What is the net charge of this? Please look at all the diagram available and check it. What should be the net charge? N-type, shall I say negatively charged or no? Sir, corresponding to this blue color, how many blue bubbles are there, circles are there, corresponding to that 6 I'm showing it. And what is these electrons? That has come due to addition of one impurity atom. So therefore, how many free electrons are there? Those many donor ions will be there. So what is the net charge of N-type semiconductor? Will be 0. I'm not showing these free electrons here. Okay, are you able to get this one? These free electrons that are generated due to thermalization is not, I'm not showing that one because their number will be far less compared to this donor ions, electron generated donor ions. So altogether, what are majority carriers? The electrons in N-type semiconductor. Minority carriers are holes. Then if I go and check it now, the product of these two, N into NH will be Ni square. I know Ne. So this you can neglect. This will be very small. No, how many donor ions I added? I know it. For addition of one donor atom, pentavalent impurity atom, one electron I'm getting. So with this, can I calculate the minority carriers? Yes, it will be. So what is the eta H concentration of holes? This is the concentration of the electrons. So approximately what happened? How many donor ions that I added? Those many free electrons will come. So you don't bother this one. This number will be far less. You can neglect it here. So as far as our discussion concerned, so what you can write? ND, number of donor ions should be equal to Ne approximately. So how much of impurity atom I'm going to add, I'll tell you. With that, you're going to calculate Ne. Then you know intrinsic carrier concentration. What is intrinsic? Yesterday I defined it. Number of electrons per unit volume in conduction band to number of holes per unit volume in valence band. This will be given for a given material, either germanium or silicon. This is a fixed value. So we'll get this one. So like this, we'll come to know how many holes are present. There's one formulas are there, just go for it. Okay, this is about the N-type semiconductor. What is the state of, if you give slight energy, what happens? These electrons are available for conduction. If you give just this much of small energy. Earlier what happens? You should pull the electrons from the valence band. But here what happens? Slight energy if you supply, as they're available for conduction. This is about the N-type semiconductor. So now we'll go for P-type semiconductor. Let me